If you map out the entirety of human history, from the first sharpened rocks to the silicon chip, the proportional weight is staggering. 99% of our timeline took place entirely within the Stone Age. When placed next to the apex predators of the Paleolithic, the human biological mismatch is obvious. We lacked thick hides, sharp claws, or the sheer muscle mass required to fight off a saber-toothed cat or a cave bear. So how did a slow, physically limited ape manage to survive this brutal environment, let alone expand across the entire planet? The answer lies in how our ancestors bypassed their biological constraints. They began engineering external extensions of their own bodies and minds. Examine the margins of this ancient handaxe. These sharp edges were fractured and shaped through a highly deliberate, repeatable manufacturing process. We stopped waiting for millions of years of natural selection to give us fangs or claws. We manufactured them instead. Physical weakness wasn't our only deficit. In an environment filled with nocturnal hunters, falling into a deep, uninterrupted sleep was an enormous biological risk. The mastery of controlled fire provided a reliable safety barrier. It kept predators at bay, carving out a pocket of security in the dark. This chart shows the biological result of that security. With the threat of being eaten reduced, humans could safely spend 25% of their sleep cycle in deep REM sleep. For comparison, apes max out at 15%. That extra REM sleep specifically strengthens procedural memory, the cognitive function that allows the brain to process and retain complex, multi-step physical tasks. Fire provided warmth, but by facilitating a more complex sleep cycle, it enabled the human brain to relate multiple concepts to one another, the mental state required to imagine and execute intricate, multi-step inventions. When it came to hunting large game, our ancestors faced another physical limit. A hand-thrown spear requires the hunter to get dangerously close to the target, and the human arm alone cannot generate enough force to pierce thick animal hides consistently. The mechanical solution was the atlatlat, or throwing board. It is a short wooden shaft with a distinct hook designed to hold a lightweight dart. This biomechanical schematic illustrates how it works. Gripping the handle and placing a dart against the hook acts as a lever, artificially extending the human arm by 50 centimeters. That extra leverage creates a massive mechanical advantage. A hunter can hurl a dart up to 90 meters, a 40% increase in range, while generating 65% more impact force. This advantage weaponized human muscle to penetrate steel. Aztec warriors utilized these darts to pierce the metal armor of Spanish conquistadors, maintaining a technological edge. Relying entirely on following animal herds is a dangerous gamble. Nomadic hunting leaves a population highly vulnerable to sudden shifts in weather or animal migration patterns. To create a stable food supply, early humans needed to hack their ecosystem. The submerged late Mesolithic site of Tybrin Vig, located off the coast of Denmark, reveals their solution: a permanent, specialized extraction industry. Here, archaeologists uncovered 10-meter-long dugout canoes designed to navigate the coastal waters. Remarkably, these wooden vessels featured clay hearths built directly inside the hull, allowing hunters to maintain fires on the water to attract nocturnal fish. The hunters operated an incredibly precise toolkit. They used long, multi-pronged spears called lysters to strike fish in the soft mud, deployed barbless bone hooks for active line fishing, and constructed extensive wooden weirs to trap migratory species near shore. By combining specialized vessels, marine traps, and artificial light, they built a reliable, multi-terrain food network. This allowed human populations to stop moving and laid the physical groundwork for permanent, sedentary communities. When we think of major technological leaps, we usually look to the heavy steel mechanics and coal-fired engines of the Industrial Revolution, or the massive computer mainframes and silicon architecture that followed decades later. These machines create a mental distance between our modern lives and our ancestors' physical reality. Yet the most vital engineering achievements didn't happen in a modern laboratory or a 19th century factory. They happened thousands of years earlier, out in the wild. Every tool we manufactured, from the atlatl to the semiconductor, functioned as an engineering project designed to reconstruct the modern human.